Okay. Thank you, Diane, and thank you, Sairaj, for the introduction. And happy to be here. I was going to start by introducing ourselves, but that won't be necessary since you already did it. So we're happy to be here, with you all talking about, these perspectives on grid forming resources. This is the agenda of what we're going to be covering today. So I'll get started on the first, 3 items of the agenda, and then that you can see here, Sebastian will cover the last 3 items, and then we'll close on UNIFI. So I'm going to be talking a little bit about, give you a quick introduction about GE. Why are we talking about inverter-based resources, right? Isn't GE like the company that does all these things? So tell you where inverters fall into the GE company. I'll talk a little bit about the energy transition, our journey and our experience into inverter-based resources, and then about some of the challenges and achievements that we've had. And then Sebastian will cover some converter control design considerations for the large fleets that we manage. That will be one of the key topics that we want to communicate in this presentation, right? The fact that, if we want to decarbonize the world, it means it involves large fleets of both wind and solar. What does that mean for the industry? He'll talk a little bit about our experience with grid forming technologies for both wind and energy storage, and then comment on some of the performance requirements, and then we'll close with some thoughts and remarks on UNIFI and how we can help the industry. So with that, I'll get started. With this quick introduction to GE, I'll be real quick, and I think you might be able to see this. There you go. So GE right now is formed by 4 different companies. There's a power business that designs and manufactures gas turbines and other types of turbines for, in general, fossil fuel generation. We have a renewable energy business, which is the one we're going to be focusing in today. There's an aviation business that designs and manufactures engines for airplanes, both commercial and military. And there's a healthcare business that designs and manufactures equipment for diagnostic healthcare. So all of the imaging, MRIs, scanners, ultrasound, and so on. There's been a recent announcement that GE is going to be splitting in 3 separate companies. So for the healthcare business will spin off first as a separate standalone business. And then there will be, after that, a spin-off of an energy company that will be combining what power and renewable energy are today. And then, finally, it will stay an aviation business will remain. So that's all to be determined, what happens going forward. But, it's 4 of these businesses today, and we're going to be providing the views of our experience with renewable energy. So let's double click on that comment, right? And let's see what's inside our renewable energy business. So we have right now 7 verticals. The first one you can see there is onshore wind. It's the largest of our businesses. We design and manufacture onshore wind turbines. We have a large fleet. This business started in 2002 with the acquisition of Enron Wind. And right now we have a fleet of over 50,000 wind turbines installed around the world. So, if you make the numbers, it's easy to see that we're manufacturing and installing around 3,000 turbines, north of 3,000 turbines every year. So that means from an inverter-based resource standpoint, that's 3,000 converters. And when you think about it, and it will be one of the ideas we talk about today, it really becomes product design. It's not a onesie, twosie type of design. It really needs to be serial design, serial production. It involves a lot of testing and validation. It includes certification for different regions, and maintaining a fleet like that, it needs, sustained availability and reliability. So that's where we're going to be making most of our comments. We also have an offshore wind business, which is in its infancy for GE. We got into it recently. We think we disrupted the industry with our launch of the Haliade turbines, which really has brought the whole industry into a new dimension of dimensions. These turbines have grown exponentially large. We have an LM wind turbine, wind power business that designs and manufactures blades for wind turbines. We have a grid solutions business, digital services, a hydro business, and last but not least, we have a renewables hybrids business. And this is kind of a small startup within GE that focuses on developing baseload power from renewables, really. So it's how can we combine solar, wind, and energy storage to provide baseload renewables. So here you can see that, here in the hybrids business, we have the energy storage, the solar experience, we have grid solutions. Our wind business is a lot of power electronics and grid integration expertise, which is what we're going to be talking about. So a few quick data points from our renewables business. I won't touch on all of these, but you can read through them, It's a $15.6 billion business. This is a couple years old figure, but presence in over 95 countries, 40,000 employees. More than 20% of the global energy capacity is provided by G-turbines. We have a fleet of 400 gigawatts installed around the world of renewable power. More than 50,000 wind turbines installed. First offshore wind farm in the US. So a lot of these, these data points just to talk about the whole industrialization of renewables, which we're going to be focusing about today. So I'm going to start really by starting with an overview of the renewables history. Very simple, very simplified view of the renewables history, right? And I'm splitting it in three different stages, right? Before the year 2000, between 2000 and 2020, and after 2020, right? So before the year 2000, really renewables, both wind and solar, were experimental technologies. It was like, a game of developing a clean technology, seen by many, as a game, something experimental, research. So cost didn't really matter. It was mostly driven by, a lot of government funding, research type of funding, and very experimental. And from the grid perspective, it was, it was just like, okay, whatever you're doing, don't bother us, just disconnect if something happens. From the year 2000 to 2020 has really been the explosion of renewables as a business, right? So the volume of installed capacity has become very significant. It has become a business driven by the levelized cost of electricity. We're going to talk about what that is in a second. That has really driven competition, not only within the wind industry, not only within renewables, but also with other power generation technologies, right? And then from a grid perspective, this growth of renewables as a business has driven, a growth in penetration of renewables in different systems. And then, things have started to matter, right? So grid companies have started to worry about what that means. And we have a page to talk about that later. So requirements have grown in complexity in those 20 years. And then after 2020, which is where we are right now, I think we're just starting a new era of grid technology. I think everyone on this call thinks that renewables are going to be the key player in the energy transition. We think that 80% or more of all the new orders we will have in the next 10 years will be for renewables. There's other drivers beyond LCOE that drive the adoption of renewables, like mostly decarbonization, right? If we need to decarbonize the planet, that means that we need to build renewables at scale. And renewables have to be industrialized, right? And then from a grid perspective, renewables are becoming the disruptor of the grid. So the grid was created around, synchronous machines and now just wind and solar running through power electronics. So we're going to be completely disrupting everything in the grid space, from, grid codes and some of the, guidelines that we have to influence and develop in UNIFI to the electricity markets as well. So everything is going to be disrupted. So this is how I think about the energy transition and the history of renewables. So very young industry, but we're in a super interesting moment of our history to see how everything's going to change. And then with that in mind, a small issue here. Sorry, not sure what's going on. I couldn't flip the page. But I'm going to talk about those two things I spoke about in the prior slide. So the levelized cost of electricity and what that's meant for wind turbines, and then the grid integration, requirements and achievements in these last 20 years. So what is levelized cost of electricity? So levelized cost of electricity, this is a slide from IRENA. You can see the formula here on the upper right. It's all the expenditures, all the expenses that a power generation plant has in its operating life, divided by all the energy it produces in its operating life. So it's a technology agnostic value to compare different power generation technologies. So this can be applied to wind, to solar, to nuclear, to gas, to whatever you want. So what's in the numerator? You can see all the expenditures, which includes the capital expenditures, the CapEx, and the operational expenditures, or OpEx. CapEx includes all the cost of the wind turbines in this case. It also includes the cost of all the balance of plant, foundations and cables, and the substation and so on. Cost of capital. And it includes, and the lifetime of the project, of course, plays an important role there. And then the operational expenditures is all the costs you have to operate and maintain the plant. In the denominator, you have the annual energy production, or AEP, which of course depends on the power curve of your wind turbine and the wind speed and environmental conditions of your site. And we're going to double click on this concept of LCOE one more. And we're going to see why that matters for turbine design and why this is important when we talk about also grid integration of renewables. So starting here with the left-hand side of the slide, this is the same formula that we had in the prior slide. And as I said before, the cost of the wind turbine is buried within this CapEx term. But if you look at annual energy production, that's really the product of the power curve of the wind turbine by the wind side distribution. So the power produced by the wind is proportional to the air density, it's proportional to the cube of the wind speed, and it's proportional to the area, to the swept area of the rotor. So once you pick a site, you're really determining what the air density is going to be like. You're determining what the wind speed is going to be like. So really your ability to impact the energy production comes down to the power curve and to the rotor, right? So this power curve is proportional to the square of the length of the blade, right? So the easiest tool we have to reduce LCOE is really to increase the length of the blade. And that's why turbines have grown so dramatically in the last, since the growth of renewables, and when, renewables really started becoming a business. So this is a comparison of our wind turbines, in 2002 and in 2020. These numbers here at the top in bold letters represent the first number is the nameplate rating of the wind turbine in megawatts. So this is a 1.5 megawatt machine. This is a 4.8 megawatt machine. The second number is the rotor diameter of the turbine. So this is 70 meters, and this is 164 meters. The third number is the tower height. So 65 meters versus 161. And you can see that all three numbers, right, in 20 years, we have more than doubled, in some cases, almost or more than tripled these numbers. We've been able to increase energy production by 400% and to decrease levelized cost of electricity by 70%. This is a trend of the whole industry. It's not just GE, these numbers here. But really what this means is, first of all, what's the driver of turbine design? It's been LCOE. So now we can say wind energy is the lowest LCOE technology that we have today. And that's been done by growth of the length of our blades. It's been a very fast growth, in just 20 years, these dimensions. And the impact is this really brings new dynamics to how wind turbines are designed and how they operate. I'm going to pause it here, and I will retake this concept because this growth of the machine, why is this important? And then I'm going to jump to the other topic I was mentioning before, which is grid integration. This slide shows the evolution of grid requirements and also of accomplishments that we've had, let's say again in the last 20 years or so. So as I was saying at the beginning, right, before 2000, again, this was all an experiment. Don't worry too much about it. If something happens in the grid, you just disconnect, no worries. Then, some utilities started saying, hey, we wish you would consume this much reactive power. Can you operate at unity power factor? But it was really in the year 2003 when, I think grid requirements for renewables in general, for wind specifically, started changing dramatically. So 2003 was when E.ON published their guidelines for low voltage right-through for wind turbines, and that really started driving more and more complicated requirements from there. Started in Germany, and then multiplied very quickly across other countries in Europe, in the US and everywhere else. I would say from that year, I think on the GE side, we really looked at how can we convert wind farms into power plants? How can we have our customers understand that a wind farm is just a power plant? And I think we were really a pioneer in developing some of the capabilities that came after that, and that were reflected in requirements later on in the grid. So for example, we developed a plant controller that allowed us to do things like voltage control, or later on we did frequency control. We also developed some new capabilities for our wind turbines, like wind-free, the capability of providing reactive power when there wasn't any wind. We developed wind inertia, synthetic inertia for wind turbines, and a lot of new technology. So I think those were great years that allowed the growth and provided confidence to our customers that wind was not going to create problems, but it could actually help the grid. I want to highlight this step here in around 2010, where we started installing more complicated and more difficult projects in remote areas of the US, Canada, Brazil, with a very weak grid. So I think I've heard some comments about people saying, hey, you're going to need grid forming to be able to have inverter-based resources operating grids with a short circuit ratio of 3. We actually have plants that we installed in around 2010, where we've been able to have inverter-based resources operate with a grid following mode with short circuit ratios as low as 1.3. And those are industrial plants that have been working, no issues in the last 10 years. After that, you're all familiar with some of the newer requirements for renewable resources, fast frequency response, multiple low voltage right through, IEEE P2800 being approved and coming our way, new grid codes in the UK, and grid forming, which is something that we will have to shape, as part of this. So really, it's been a tremendous, if you just look at this picture, and if you combine the growth in size of the wind turbines plus the growth in complexity of the requirements, it's really been, I think, amazing, the growth of this industry. And I'm going to close my section, by connecting this to this great article from NREL that was published a couple of years ago, talking about the 3 grand challenges of wind, which is, one is understanding the wind, the second is the structural and system dynamics, and the third one is grid integration. And with these complicated grid interconnection requirements, and with the growth and the size of the turbines, all these 3 become completely interrelated. So you cannot do one without the other one. So, when it comes to designing these converters, is no longer like an ideal voltage source with an ideal, DC link that is, now I can do whatever I want with it and create, and have a grid forming control. You really need to worry about what's happening on the other side of the converter. What's happening with that solar panel if a cloud is coming? What's happening with, a wind turbine if it's going through a certain type of event driven by the wind or by something else? So we wanted to. I'll let you with this thought, and then I'm going to hand it off here to Sebastian, who's going to get more into the details of the converter design.
Thank you, Pedro. That's great. So, can you hear me well?
I can hear you.
Okay. So now I'm gonna narrow the discussion a bit. I think it was great that Pedro went from higher level, and then he started narrowing to specifics of wind turbines and electrical requirements. Now, this will further narrow the discussion into some considerations of product design for large inverter-based resources fleets. So if you have, like Pedro's mentioned, if you have a wind turbine product that is sold by 3,000 per year, how are the processes around designing those products? The reason why Pedro and I thought it was useful to talk about this is in the context that some of the objectives of UNIFI is to support OEMs in aspects related to algorithms of grid forming. So this process is related to product design have changed with the years and with the different requirements in recent years, let's say. So on one side, we have the product design is now focused on a particular project, is focused on the thousands of products that will be deployed. So for that reason, during the product design effort, you have to look at the different grid conditions that are expected. So you don't know exactly what are the exact grid conditions of each one of those wind turbines, but you have to use the understanding of the typical ranges, the specifications of the products, and based on that, you define the different grid conditions for purpose of a design. You will also consider the different performance expectations, in the sense that there are different grid codes in different countries and different states. You have to consider that for the design. That is, you don't design a product for ERCOT in the US and a different product for AMO in Australia. You basically design one product that is useful, that is intended to be used in all the markets where it will be sold. Other aspects that are kind of hinted already, but it's very important, is that at the time you're designing the product, you don't really know the plant in which it's going to be deployed. So that is a particular characteristic of inverter-based resources. Other points are related to the relatively short cycles. So the products don't last for 10 years, the product lasts for 2 or 3 years. After that, you basically need a new product to stay competitive. So this product design cycle is done over and over again every couple of years. And in fact, you tend to have like more than one product line for a particular business. So you will probably have more than one product being designed at the same time. The grid requirements, so how these wind turbines or the solar inverters behave or manage to meet grid requirements, has typically been mostly related to converter controls or potentially converter ratings. Now, that is changing as the grid code requirements get more involving. We see how there are more controllers that are affected and more hardware that is affected. The picture in the right shows the typical controllers that you find in a wind plant. There's similar for other types of inverter-based resources. So at a turbine level, you have a converter control, a turbine controller, and then at a plant level, you have a plant controller that Pedro mentioned how we added functions like many years ago for it. So the grid requirements are impacting beyond the converter control. We see how the turbine control is becoming more and more relevant as we see frequency events or expectations regarding the response of inverter-based resources to frequency events. The turbine control becomes more and more relevant, and the plant level control has been relevant for many years in terms of controlling voltage at the point of interconnection or frequency or power at the point of interconnection. In general, so because when you design the product before you know the plans, you could kind of take a couple of options here. You could say, well, I'm going to design a basic product and then I tweak this product for every plant. Or I'm going to design as many options in this product as possible so that I minimize the amount of application engineering or tweaking that I need at the time of the wind plant being deployed. So the second option is where the industry in general is going. I don't think this is a GE thing. The product design has significant complexity and significant, let's say, effort to try to reduce the amount of effort at the time of deploying plants. This has enabled really the massive deployment of inverter-based resources. Maybe we can move to the next slide, Pedro, if you don't mind. Thank you. Furthermore on this, so once you decide all the system conditions that you want to evaluate your product on, you go through the design process and then you do the verification. So on the right, you see like a general process. You start with the performance requirements, and then you go to product specification. In modern years, performance requirements have got more complicated, and it's not like you need to drive through a voltage sag down to 20% or down to 0% for 100 milliseconds. It got a lot more complex in the sense that during a particular type of simulation or scenario, your reactive current has to do this, your active current has to do that, and then on top of that, you shouldn't trip. So the performance requirements reflect that type of complexity these days. From those requirements, you specify the product, you go through the product design, and that will have a hardware and a control aspect. And then there is sort of a prototyping and design validation. There is more than prototyping. The design validation is more complex and has the aspects that are mentioned in the first bullet on the left. So there is a significant amount of simulations, hardware in the loop simulations, embedded-based resource tests at a lab environment with the electrical equipment only, and then prototypes with, let's say, the full turbine or the full battery system, for example. This performance evaluations get quite complex. In the past, we used to check if the equipment would trip or if the equipment will get damaged during the design validation. These days, we have to check that we meet all these performance requirements in terms of how the reactive current, the active current behaves, or how the DC components get reduced, or the negative sequence behavior is acceptable. All of those things are part of this design validation that are done at the product level. And really, one of the main complexities that we're seeing with this energy transformation is that you need to comply with all these things at the same time. That's maybe obvious, but when you are verifying compliance to all these requirements, it's relatively common that you would do a modification in the product to meet a particular requirement where you have trouble, and by doing that, you solve the problem that you're trying to address, but then you create a different problem with something else. So you have to continuously do these verifications that you are not having unintended consequences of the changes that you perform. So all of that is part of the product design. In addition to that, as you can imagine, the requirements around the world are not consistent. So different places require different things. In addition to that, different electrical conditions require different things. For example, you could find that a particular place requires the active power to recover very quickly after a fault. A particular country or grid code may require that. At the same time, if you have a short circuit ratio that is extremely weak, for example, like Pedro was describing, short circuit ratio 1.3, you may not be able to recover power so quickly because otherwise the system collapses. So you actually need to have features that can be configured differently for different applications. So you verify that your product is able to cover the different requirements of the different grid codes and the different type of grid conditions that you expect to deploy these products in. And you may define different parametrizations of the product to meet all those different requirements and conditions with the same product. After you have all of that at the product level, only then you start using this product in different applications with the idea that the application engineering, so in that, if you look at the diagram there on the right in the lower part, it shows that once the product is sort of designed, you will apply it in different projects at the same time. The application engineering work to apply the product is significantly less than the efforts that were done to design the product. And that is obviously intentional. Now, in the context of grid forming products, it is expected that the grid forming products will have to have similar type of processes as this process I described that has been applied to grid following embedded-based resources products. At the same time, it is expected that the grid forming algorithms are actually a subset of all the control functions and protection functions in an embedded-based resource. So in a way, you would most likely, at least that's what we are seeing, you take a product that is grid following and you modify its controls to add the grid forming features. And by doing this, you may have all these unintended consequences on other things that were working that you have to address. But fundamentally, you're going to try to reuse as many of the features that were already created with grid following related to aspects that do not contradict the grid forming features. So I think that that's an important consideration. So very often when you want to modify some of these very complex, massive codes in converter controls that were designed to meet all of these requirements at the same time, some of the more complicated aspects is to understand what is already in the product before you can modify it. So let's go to the next slide if you want, Pedro. Switching subjects a little bit. So the previous slides were about the experience with large fleets and converter control design considerations. Now, moving a little bit to our experience with grid forming. In this particular slide about grid forming batteries. So GE had the possibility and request to provide systems with grid forming characteristics with batteries. We listed the key projects here. You can see, so first bullet is most of the BESS projects are not grid forming. I think you guys know that, but the industry sometimes misses that point. In terms of which battery projects are grid forming, you see in the slide a few projects listed, and some of them are from 1995, 1996. Those were the initial ones. Those were actually done with GTO, so the power electronic technology was really old compared to what we have available today. But the controls were grid forming, and these converters had the characteristic that they were able to maintain a system stable without presence or significant presence of synchronous machines. Those systems that were very, it was a significant contribution at the time. We didn't see customers asking for this for many years. In 2017, we got an opportunity to apply some of the concepts that, well, I wasn't involved in the 95, 96 projects, but that GE came up with in those years in more modern IGBT converters and more modular solutions as well. So in 2017, a 1.25 MVA converter with a battery was adapted to have grid forming characteristics and was used to black start a gas turbine. Black starting a gas turbine is really like black starting an industrial plant. You basically have to energize all the auxiliary services that are motors, drives, that are required to start a gas turbine. So that's what we did in 2017. After that, there were a few projects like that that we did with different characteristics. Some of them have large motors like the one we did in 2017. Some others had large drives like the one in 2019. And then the one that we did in 2020 was we were able to do something similar to what we did in 2017, but with significantly lower rating in converters as we gain confidence in the behavior and response. After that, this business, GE Hybrids, has moved into creating a second version of grid forming products. So we're moving to more modern converters, and those are already designed to have grid forming features as well. So in these projects that are mentioned here, the projects demanded black starting of the industrial system, as I mentioned before. The black starting operation had to be demonstrated, so you actually have to black start the plant. So it's no kidding. It's not only simulation. You have to really show that it does that. And then all of them were deployed with modular solutions and distributed batteries, in the sense that you have several, let's say, 10, 15, 30 converters that will operate individually, independently, performing the grid forming controls to be able to have the full plant black starting. So in that sense, that is related to what we expect to see in interconnected systems, where you have more than a single inverter performing the grid forming features. You already have a distributed grid forming sources in a system. So the controls, we believe that the controls that were developed for these functions are compatible with the grid forming features that are expected, are being discussed for interconnected grids. Pedro, if you don't mind, maybe we can move to the next slide. We brief in this one. So this one highlights some of the challenges related to this grid forming projects. Large drives fed from batteries was a significant challenge. We have LCI drives, so line commutated inverters with thyristors of similar rating as the batteries, being controlled from the batteries. So there was a lot of room for power electronic interaction there, and harmonic and power pulsation interactions that had to be addressed. Some of the other cases where we didn't have the large drive, we had very large asynchronous machines that had to be directly started. So as you know, asynchronous motors have a very large inrush current, so you have to feed like 3 times their rating in reactive current in order to get them to speed up. So doing that from a battery was quite challenging, particularly if you want to keep the rating of the battery to be limited. So managing the current limitations of the power electronics and at the same time keeping the grid forming characteristics so that the system wouldn't collapse was an important part of these designs. Transformer energization was also a consideration. Some of the projects, some of the transformers that were energized together with the batteries, like a soft start of the transformer to avoid their inrush currents. But in some cases, we had to look at energization of transformers, like a standard energization, and dealing with the inrush of the transformer, as you can imagine, is a challenging activity from an inverter. So that was part of the design considerations. One aspect of this project, though, just to close this, is that the performance requirements were extremely complex. So in this case, the performance requirement was have a battery system that can start this particular industrial system with this motor and that drive. So the definition of requirements in a more general way, trying to say, well, grid forming should have this and that feature, is actually very, it's more difficult than this particular plans, because you have to generalize it. And also details in the requirements drive significant differences in the design of the system. So in particular in this battery systems, small details in the way we would be allowed to start motors will have a significant impact in the current rating we needed in the inverter-based resources. So performance requirements have a significant impact in the design for grid forming, and the requirements are not easy to define, as you know. Pedro, maybe we can move to the next slide. Thank you. Talking a little bit about grid forming onshore wind turbine. GE has been progressing in this subject. They've been working for a few years now in developing controls and adapting the hardware, the existing hardware, to have a double fed induction generator with grid forming performance. The design has been designed and demonstrated to a good extent. We have performed extensive hardware in the loop and standard simulations. There have been electrical tests of the electrical system performed in NREL facilities, where we got the chance to work there with the NREL team in evaluating key aspects of grid forming technology that I'll mention in a second. And then, of course, we also did a number of demonstrations and performance tests in GE facilities in our laboratories. The evaluations of performance cover a number of things. Maybe of particular relevance is the inertial response and response to phase jump. That was a key aspect of grid forming, and we tested that in all of those ways. We also looked at other frequency events like sustained frequency excursions. And then we also looked at voltage sags and fault behavior of balance and unbalanced types. This was helpful to fine-tune the controls, and we were able to get performances that sort of support this idea of operating systems with lower number of synchronous machines in the system. One comment there at the end is related to the overload capability. The doubly fed induction generator tends to have a larger overload capability, which is quite beneficial to respond to grid forming in the grid forming way. avoiding like significant curtailment, for example, or allowing for transient excursions of, for example, active power without significantly overrating the equipment. So that has been a good to verify that. Let's go to the next one, Pedro, please. Thank you. This slide is a little bit complicated, but not complicated. It tries to touch many subjects. I will give it a try. In the discussions about performance requirements of grid forming, we are seeing, as I know the UNIFI team is seeing, and probably the people in this call are seeing, quite a bit of discussion, like in different places. Different entities are expecting different things from grid forming. For example, we have occasionally developers contacting us with a particular problem that they have, that the grid is very weak and they want to use grid forming to solve the problem. Or we see very useful discussions also with transmission companies or reliability entities that are thinking of requiring grid forming features, and they're trying to see in what context they should be using it and what are the improvements that they should expect. So in that context, we propose here to divide some of the problems that are related to high penetration in inverter-based resources in two types of problems. The one in the left is what we would refer to as power transfer challenges, where you basically have a plant, it could be a solar plant, a wind plant, or it could be a number of plants in a remote cluster that connect through a long transmission line or system to a bulk power system. So this is one way of defining weak grid. This is one type of weak grid. And then on the right, we have a different problem, which is you have a number of things where you have wind plants, maybe some synchronous generators, some other plants, and loads, all in that region that is weakly connected to the rest of the system. The system on the left, we've been discussing for many, many years. The system on the right is kind of what we're starting to see more and more often, and it's one of the worries that are triggering some transmission companies or reliability entities to talk about weak grid, grid forming. So we want to differentiate the two and mention a couple of things related to this. With the system on the left, there are grid following inverter technology that has been designed to operate with problems like this for many years, like Pedro was describing. There are some grid followings that perform very well in this, some other grid following that may not perform as well in this. It depends how they're designed and the particular interest of the OEM. Now, in the systems, there is an intrinsic limitation of the transmission line of how much power you can get out of the inverter-based resource plant. It doesn't matter if you have a grid following plant, a grid forming plant, or a synchronous machine, that limitation exists. And the grid forming features in a wind plant or in a solar plant are not going to necessarily overcome that, right? So there are some limitations intrinsic to the long transmission system. And even if you go beyond that, even before you get to that limit, the sensitivity of active power and reactive power to voltage gets really hard to manage. And that aspect makes the inverter-based resources or a synchronous machine tend to go unstable close to those limits, steady-state limits of the transmission system. So in this type of problems, grid forming technology does not have a characteristic advantage with respect to grid following. So it would make sense to try to design grid forming systems to have at least the type of performance that we see in the advanced grid following concepts. But we shouldn't expect to see too much more because there is not a characteristic advantage of grid forming in this case. Now, when you look at the problem on the right, it's very different. So with the problem on the right, you have a system that you expect to have large, for example, angle fluctuations because you don't have significant synchronous machine close to these loads and these inverter-based resources. Or you would expect if the complete interconnected system has these characteristics that there will be significant rate of change of frequency unless your inverter-based resources have grid forming features. So grid forming has a characteristic advantage over grid following for this type of problems related to minimizing angle fluctuations, pushback on the rate of change of frequency, and also if the short circuit ratios gets really low, let's say 0.3, 0.4, 0.5, the grid forming will be able to avoid some instability risks that you see in grid following inner loops or interactions at extremely low short circuit ratios. So this problem on the right is not related to pushing power through a weak connection. It's more related to keeping the system stable in terms of other aspects beyond transferring power. So the problem on the left is the old problem, I would say, but we still have it. The problem on the right is the new problem. In the field, we tend to see combinations of the two. We see that from the point of view of performance requirements, it makes sense that grid forming has performance requirements that go way beyond what grid following is requested to do for aspects or problems related to a system on the right. We don't expect that the grid forming products are going to perform significantly better than grid following, at least advanced grid following, for the problem on the left. Okay, maybe we move to the next one. I took a lot of time in that one. So some final remarks, and here, Pedro, feel free to join. I will try to represent this conclusions, but feel free to chime in. So we're very excited to have the chance to talk today, but also to be part of the UNIFI consortium. We believe that UNIFI has a unique opportunity to support the industry in assimilation of grid forming technology. For example, we see that the guidelines to the industry in how to use this technology is key. We see that there is some oversimplification sometimes of where can grid forming help and when can grid forming do something similar to what it was there before. So that guidance from UNIFI can be very helpful to make the use of the technology effective. In terms of reliability entities, standard setting bodies, and OEMs, clearly UNIFI has the possibility to help sort of define requirements, hopefully functional requirements of what grid forming should be able to do in the system. And this consistency in requirements will definitely accelerate having the relevant technology ready, because OEMs then can work on consistent requirements and we can be more effective. And then also the evaluation processes from the point of view of a system operator are more consistent because the requirements are more coherent among different places. Moving to the next bullet, this is something that we mentioned before. Grid forming control algorithms are likely to coexist with legacy features of GFL within a particular IBR design. So grid forming is going to be like a modification of certain algorithms, but many of the algorithms in this very complex products are going to stay. So the game of coming up with grid forming controls is not only about the new algorithms that we add, but at least for OEMs, it is also with the understanding of how the products are, then how we assimilate these new control modifications. I would say maybe even 70% of incorporating new algorithms is related to understanding the ones that already exist and how the new stuff affects the old stuff in the product. Next bullet, grid forming inverter is not sufficient for grid forming inverter-based resource. And Pedro addressed this subject. We could see the grid forming inverter, assuming that you have a perfect DC link and you basically define all the grid features of an inverter to have the performance that will help the grid is part of the problem. It's not enough, right? Dealing with the limitations of the equipment in terms of current capability, in terms of extraction of power capability, effects in the drivetrain, in the mechanical system, all of those things are also part of creating an inverter-based resource that go beyond the grid form inverter itself. That is something that is relevant, and I'm sure the UNIFI team is looking to address that within the possibilities, right? The final point, I think this is related to some of the areas of work that you have defined. Facilitating models, modeling platforms will definitely help accelerate the understanding. We see that the industry is learning through simulation models. So providing models so that the industry can sort of play around and see what are the advantages of the technology, how it can be used for particular problems would definitely help. And that's also something that UNIFI is addressing. Pedro, I don't know if you wanted to add something to
You covered it great, Sebastian. Thank you so much. I think the only thing I will add is, as Sebastian said, we're super, proud to be part of UNIFI. I think our goal is all the same, which is, the decarbonization of the planet, and that's, that has to be done by industrializing really renewables and driving these large fleets of inverter-based resources, and hopefully we're able today to share with you some of the challenges that we have, when we do that as part of our, daily works, our daily jobs. And, and there's many other challenges that we're going to have to overcome as well. So the more we can keep it simple, the more we can try to fit, our guidelines within the existing, framework of how we operate today, I think it will help the industry to, to progress faster, which is our goal. So I think that's it from our side. So Cyrus, back to you in case there's questions.
Thank you so much.